Welcome to G Fun Facts Online. Imagine looking back in time, so far back that you're witnessing the birth of the very first light in the universe. This isn't science fiction. It's what the James Webb Space Telescope is doing right now. And what it's finding is forcing us to tear up the textbooks and rewrite the story of our cosmic origins. This technological marvel is peering through billions of years of cosmic history into a mysterious period called the Cosmic Dawn, a time when the universe, once a vast expanse of darkness, was first set ablaze by the light of the very first stars and galaxies. And at the heart of this primordial revolution, Webb is unveiling a startling revelation: the existence of colossal black holes, far larger and far earlier than our theories ever predicted. These aren't just record-breaking discoveries. They are a fundamental challenge to our understanding of how the universe's most enigmatic objects, and indeed the cosmos itself, came to be. For decades, the Cosmic Dawn was a tantalizing but inaccessible frontier. This period, which began roughly 100 million years after the Big Bang, marks the end of the cosmic dark ages. During this epoch, gravity began to pull together the primordial soup of hydrogen and helium, igniting the first stars and assembling the first galaxies. This era set in motion the processes that led to the complex universe we inhabit today. But it remained largely theoretical, hidden behind a veil of time and distance. Now, with its exquisite sensitivity to infrared light, the James Webb Space Telescope is pulling back that cosmic curtain, allowing us to witness this pivotal chapter in universal history firsthand. And the story it's telling is truly mind-bending. Since it began its mission, Webb has been systematically identifying galaxies at the farthest reaches of the cosmos, pushing the boundaries of observation deeper into the past. And inside some of these ancient galaxies, astronomers are finding active supermassive black holes that existed when the universe was just a toddler. Let's talk about one of the most remarkable of these, the galaxy GNZ11. This galaxy was initially spotted by the Hubble Space Telescope, but its exceptional brightness was a complete puzzle. Webb's powerful instruments took a closer look and provided the first clear evidence of what was powering it: a central, supermassive black hole, vigorously consuming matter. The incredible part is that we are seeing GNZ11 as it was just 430 million years after the Big Bang. That's an incredibly short time in cosmic terms. The black hole at its center is estimated to be about 1.6 million times the mass of our Sun. To put that in perspective, our Sun is a single solar mass. This object is 1.6 million of them, crammed into a point of infinite density, and it existed when the universe was only 3% of its current age. Astronomers believe this black hole is accreting or feeding on surrounding gas and dust at a furious pace. This intense feeding frenzy releases an enormous amount of energy, which is likely responsible for the galaxy's extraordinary luminosity, making it bright enough for us to see from over 13 billion light-years away. But Webb's discoveries didn't stop there. Another groundbreaking find is the black hole in a galaxy named CEERS 1019. This one existed a mere 570 million years after the Big Bang. What makes this black hole so interesting is its relatively modest mass of about 9 million solar masses. Now, calling 9 million suns modest sounds absurd, but in the context of early universe black holes, it is. Before Webb, we could only detect the absolute behemoths at these distances, those containing over 1 billion times the mass of the Sun, simply because their immense brightness made them easier to spot. The detection of a smaller black hole, like the one in CEERS 1019, which is actually comparable in mass to the black hole at the center of our own Milky Way, suggests that these less massive black holes might be everywhere in the early universe, just waiting to be discovered. The galaxy itself, CEERS 1019, looks like a chaotic scene of 3 bright clumps, a strong hint that a galaxy merger could be fueling the black hole's activity and triggering furious bursts of star formation. More recently, Another Webb program confirmed the existence of a black hole in a galaxy designated Kuiper's LRDZ9, seen as it was only 500 million years after the Big Bang. This object is part of a newly identified class of galaxies called little red dots, which are compact, red, and surprisingly bright. The black hole at the heart of this particular little red dot is a true monster, estimated to be up to 300 million times the mass of our Sun. 300 million. At a time when the universe was barely 500 million years old. Its immense size, at such an early stage in cosmic history, presents a significant, almost impossible challenge to our understanding of how black holes are supposed to evolve. This brings us to the core of the issue, the cosmic conundrum. How did these black holes get so big so fast? The discovery of these ancient, massive objects has thrown a giant wrench into the standard models of black hole formation and growth. For a long time, the prevailing theory was what's known as the light seed model. The idea was that the first black holes were the remnants of the first generation of stars, known as population 3 stars. These stars, forged from pure hydrogen and helium, were thought to be exceptionally massive. When they ran out of fuel, they would have collapsed to form black holes with masses, maybe tens, or perhaps a few hundred times that of our Sun. Think of these as the light seeds of future supermassive black holes. The theory went that these seeds would then grow over billions of years by slowly accreting gas from their surroundings and merging with other black holes. It's a sensible, gradual process. But there's a problem. There's a theoretical speed limit to how fast a black hole can accrete matter, a concept known as the Eddington limit. If a black hole feeds too quickly, the radiation blasting out from the superheated material will actually push away any more incoming gas, effectively choking off its own food supply. The immense black holes observed by Webb in the cosmic dawn appear to have grown far too large in the limited time available. They seem to have completely defied this cosmic speed limit. It's like finding a fully grown 100-foot-tall redwood tree that you know was just a tiny seed only a year ago. It simply doesn't fit the known rules of growth. This has led to a surge of interest in alternative, more radical heavy seed models. One of the most prominent theories is the direct collapse black hole scenario. This model proposes that under very specific, pristine conditions in the early universe, vast clouds of gas could have collapsed directly into a massive black hole, completely bypassing the star formation stage. For this to happen, the gas cloud would need to be huge, metal-free, and bathed in a strong ultraviolet radiation field from nearby galaxies. This radiation would act like an oven, preventing the gas from cooling down and fragmenting into smaller clumps that would form individual stars. Instead, the entire, massive cloud would collapse in one go, forming a heavy seed black hole with an initial mass of maybe 10,000 to 100,000 times that of the Sun. This would give them a tremendous head start in the race to become supermassive. An even more exotic and fascinating possibility involves primordial black holes. These are not the remnants of dead stars at all. They are hypothetical black holes that could have formed in the first fractions of a second after the Big Bang from the collapse of extremely dense regions of matter and energy. Unlike stellar black holes, primordial black holes could have a wide range of masses, and crucially, they would have been present from the very beginning of the universe. The surprising discoveries by Webb have renewed serious scientific interest in this idea. Some scientists propose that these primordial black holes could have acted as the seeds for the supermassive black holes we see today, and maybe even for the surprisingly large galaxies that Webb is also finding in the early universe. The observations of galaxies like GNZ11 seem to support these heavy seed scenarios. In our local, modern universe, a supermassive black hole's mass is typically a tiny fraction, about 0.1% of its host galaxy's mass. But in these early galaxies, the black holes are proving to be much more substantial relative to their host galaxies. In some cases, the black hole's mass might be a few percent, or even more, of its galaxy's mass. This suggests a fundamentally different relationship between black holes and galaxies back then, perhaps one where the massive black holes formed first, acting as cosmic seeds or gravitational anchors around which the galaxies then grew. So how are we able to see all of this? The James Webb Space Telescope's ability to make these revolutionary discoveries is a testament to its cutting-edge instruments, which are specifically designed to capture the faint, red-shifted light from the early universe. Two instruments in particular have been pivotal in this hunt for the first black holes: the near-infrared camera, or NIR-CAM, and the near-infrared spectrograph, or NIR-SPEC. NIR-CAM is Webb's primary imager. It's responsible for detecting these incredibly distant and faint galaxies. It sees the universe in near-infrared light. This is crucial because as the universe expands, it stretches the light traveling through it. Light that left a galaxy 13 billion years ago as visible or ultraviolet light has been stretched so much by the time it reaches us that it now falls in the infrared part of the spectrum. NIR-CAM is designed to see this ancient, stretched light, and it can also peer through cosmic dust that would normally obscure our view. Once NIR-CAM identifies a candidate for an early galaxy, NIR-SPEC performs the crucial task of spectroscopy. This is where the real detective work happens. NIR-SPEC acts like a prism, splitting the faint light from an object into its constituent colors, or a spectrum. This spectrum is like a cosmic barcode, and it's packed with information. First, spectroscopy is the key to confirming the galaxy's immense distance by precisely measuring its redshift, how much its light has been stretched. Second, it allows scientists to identify the telltale signs of an active, feeding black hole. As gas is pulled into a black hole's powerful gravitational grip, it gets whipped around at incredible speeds, forming a superheated accretion disk. The light emitted by this gas gets smeared out across the spectrum due to the Doppler effect. Some gas is moving towards us, some away. This broadening of specific spectral lines is a smoking gun for the presence of a black hole. Furthermore, the intense radiation from this accretion disk ionizes the nearby gas, causing it to glow at very specific wavelengths. NIR-SPEC can detect these emission lines, confirming that the black hole is actively feeding. The combination of NIR-CAM's sharp imaging and NIR-SPEC's detailed spectroscopy provides an unprecedented one-two punch for finding and characterizing the universe's first black holes. Of course, observing the cosmic dawn is fraught with challenges. The galaxies and black holes we're looking for are incredibly faint and distant, pushing the limits of even Webb's magnificent capabilities. Distinguishing a genuine early black hole from other astrophysical phenomena, like a burst of star formation, requires incredibly careful and detailed analysis of the spectral data. There's also the issue of observational bias. By definition, the brightest and most massive black holes are the easiest ones to detect, which might be skewing our understanding of the entire population. We're seeing the exceptions, the monsters, but what about the average black hole in the early universe? Despite these challenges, the future of this research is incredibly bright. The James Webb Space Telescope is expected to continue its exploration of the early universe for many years to come. Upcoming observation cycles will target more of these distant quasars and the little red dot galaxies that host them. The goal is to build a much larger sample size to better understand the demographics of the first black holes. Were they mostly small, or were these overmassive black holes surprisingly common? Astronomers are hoping to find even more of these impossible black holes to test their formation theories with greater statistical certainty. Each new discovery from Webb is a new piece of the puzzle of our cosmic origins. The glimpse it is providing into the cosmic dawn is transforming our understanding of the universe's infancy. The so-called impossible black holes it is uncovering are not just breaking records. They are opening up entirely new avenues of inquiry and forcing us to rethink the fundamental processes that shaped the cosmos we see today. We are living in a golden age of astronomy. Webb is our time machine. And as it continues to gaze back to the dawn of everything, we can be sure that many more revolutionary, mind-bending discoveries await us. The universe's baby pictures are finally coming into focus, and they're showing us a cosmos that is wilder and far more mysterious than we ever imagined.